For more than a century, human civilization has depended on burning fossil fuels to power industry, transportation, electricity grids, and digital infrastructure. Coal drove the Industrial Revolution. Oil fueled global mobility. Natural gas stabilized modern energy networks. But this system has a fundamental flaw. Combustion releases carbon dioxide and other greenhouse gases that accumulate in the atmosphere, altering planetary climate systems. The urgency of climate change has intensified the search for energy sources that are abundant, carbon-free, and capable of sustaining industrial-scale demand. Among all proposed solutions, solar, wind, fission, nuclear, geothermal one stands apart in both ambition and complexity. Fusion energy. Fusion is the process that powers stars. In the core of the sun, immense gravitational pressure forces hydrogen nuclei together, forming helium and releasing vast quantities of energy. This energy radiates outward, sustaining life on Earth. The question scientists have pursued for decades is whether it is possible to recreate that stellar process under controlled conditions on our planet. Unlike nuclear fission, which splits heavy atoms such as uranium, fusion combines light atomic nuclei. In principle, fusion offers extraordinary advantages: abundant fuel supply, minimal long-lived radioactive waste, and no carbon emissions during operation. Yet achieving practical fusion power has proven to be one of the most difficult engineering challenges in human history. At the center of the global fusion effort stands ITER, an international collaboration involving Europe, the United States, China, India, Japan, Russia, and South Korea. ITER is not designed as a commercial power plant, but as a proof-of-concept reactor intended to demonstrate sustained net energy gain from fusion. The scale of the project reflects the magnitude of the challenge. Fusion requires recreating conditions comparable to the core of a star, not in gravitational confinement, but in engineered magnetic fields within a terrestrial facility. The fundamental physics of fusion begins with atomic nuclei. Positively charged nuclei repel each other due to electrostatic force. To overcome this repulsion and allow fusion to occur, particles must collide at extremely high temperatures and pressures. In the Sun, gravity provides confinement. On Earth, scientists rely primarily on magnetic confinement. The most advanced design is called a tokamak, a toroidal chamber surrounded by powerful superconducting magnets. These magnets generate fields that confine plasma state of matter where electrons are stripped from nuclei, preventing it from touching reactor walls. Plasma behavior is inherently unstable. It behaves more like a dynamic fluid than a static gas, exhibiting turbulence, instabilities, and magnetic disruptions. Maintaining plasma stability at temperatures exceeding 100 million degrees Celsius requires extraordinary precision. At such temperatures, matter cannot be contained by any material surface. It must be suspended by magnetic fields. Even minor fluctuations can lead to energy losses that disrupt the fusion process. The goal of fusion research is to achieve what is known as net positive energy output. This means the fusion reactions produce more energy than is required to initiate and sustain them. Historically, fusion experiments consumed more energy than they generated. However, recent experimental milestones have demonstrated brief instances where energy output approached or exceeded input under specific measurement conditions. These results mark scientific progress, but do not yet constitute sustained commercial viability. The fuel most commonly studied for fusion reactors is a mixture of deuterium and tritium, both isotopes of hydrogen. Deuterium is abundant in seawater, making it effectively limitless on human timescales. Tritium is rarer and must be bred within the reactor using lithium blankets that capture neutrons produced during fusion reactions. This closed-loop fuel cycle is essential for long-term operation. The neutron flux generated during fusion poses materials science challenges, as reactor walls must withstand intense radiation without degrading rapidly. One of the primary reasons fusion is so difficult lies in confinement time and plasma density. Achieving fusion requires a specific combination of temperature, particle density, and confinement duration. This balance determines whether reactions occur at sufficient rates to sustain energy output. Even if temperatures are achieved, insufficient confinement leads to rapid energy loss. Magnetic field strength, plasma shape, and heating techniques all influence this delicate equilibrium. Heating plasma to fusion temperatures involves multiple methods. Ohmic heating passes current through the plasma itself, but this becomes less efficient at higher temperatures. Additional heating techniques include injecting high-energy neutral particles or using radiofrequency waves to transfer energy directly into plasma ions. Each method must be synchronized precisely to prevent destabilizing the magnetic confinement. In addition to magnetic confinement, alternative fusion approaches exist. Inertial confinement fusion uses powerful lasers to compress tiny fuel pellets to extreme densities for brief moments. This method relies on rapid compression rather than sustained magnetic fields. Both approaches face immense technical barriers, and research continues in parallel to determine which pathway offers the most scalable solution. Climate change urgency amplifies interest in fusion. Renewable sources such as solar and wind have expanded rapidly, but they are intermittent. Energy storage technologies help stabilize grids, yet global energy demand continues to rise. Fusion promises consistent, baseload power without carbon emissions. Unlike fission reactors, fusion does not carry the same meltdown risk, because the reaction requires continuous input conditions. If confinement fails, the plasma cools rapidly and the reaction stops naturally. Economically, fusion represents both risk and opportunity. The capital cost of constructing experimental reactors is enormous. ITER itself represents one of the most complex scientific collaborations ever attempted. However, if commercial fusion becomes viable, the long-term payoff could be transformative. Abundant clean energy would reshape geopolitics by reducing dependence on fossil fuel reserves concentrated in specific regions. Energy scarcity has historically influenced global conflicts. Fusion could alter that dynamic fundamentally. The phrase "the energy source that could end oil" captures public imagination, but the transition would not occur overnight. Infrastructure for fossil fuel extraction, refinement, and distribution is deeply embedded in global economies. Fusion adoption would require new grid integration, regulatory frameworks, and industrial scaling. Moreover, commercialization timelines remain uncertain. Even optimistic projections place large-scale fusion power plants decades away. Materials science is central to progress. Reactor components must endure extreme thermal loads and neutron bombardment. Advanced alloys and composite materials are being developed to improve durability. Superconducting magnets capable of sustaining strong magnetic fields with minimal energy loss are critical. Improvements in high-temperature superconductors have renewed optimism by enabling more compact reactor designs. Artificial intelligence increasingly assists fusion research. Machine learning models analyze plasma behavior in real time, predicting instabilities and adjusting magnetic fields dynamically. This integration of advanced computation with experimental physics accelerates optimization cycles. Fusion is no longer purely a physics challenge. It is an interdisciplinary engineering endeavor involving data science, cryogenics, and systems control. Public perception of fusion oscillates between skepticism and excitement. For decades, fusion was described as perpetually 30 years away. This skepticism stems from repeated timeline extensions. However, recent experimental progress and private sector investment have shifted narratives. Venture-backed fusion startups pursue alternative reactor designs, leveraging advances in materials and computational modeling unavailable in earlier decades. Fusion also addresses long-term sustainability beyond Earth. If humanity establishes lunar or Martian settlements, compact fusion reactors could provide reliable power independent of sunlight variability. The synergy between fusion, research, and space exploration highlights the interconnected nature of advanced technologies. The physics of star power on Earth ultimately hinges on mastering extreme conditions in controlled environments. Unlike the Sun, Earth lacks gravitational confinement. Instead, we must simulate stellar conditions through electromagnetic engineering. Achieving sustained fusion means creating a miniature star within a magnetic cage, extracting energy without allowing the reaction to escape control. Critics argue that renewable energy expansion alone may suffice to decarbonize grids without fusion. Others contend that long-term industrial growth and global energy equity require higher density energy sources. The debate is not binary. Fusion, if successful, would complement rather than replace renewables, forming part of a diversified energy portfolio. The broader implication of fusion extends beyond electricity. Abundant energy enables desalination at scale, synthetic fuel production, carbon capture, and advanced manufacturing. Energy availability underpins economic development. Regions currently constrained by limited energy access could experience transformative growth if fusion becomes widely deployable. ITER role is symbolic and practical. It demonstrates international collaboration on a project of unprecedented technical complexity. Success would validate decades of theoretical work and justify further investment. Failure would not necessarily end fusion research, but would recalibrate expectations. Ultimately, fusion energy represents humanity's attempt to harness the fundamental forces that power the cosmos. It is an engineering challenge of extraordinary magnitude, but its potential rewards are equally extraordinary. Clean, abundant energy without greenhouse emissions would redefine industrial civilization. The path is difficult because it requires controlling plasma hotter than the sun's surface within magnetic fields generated by superconducting coils cooled to cryogenic temperatures. It demands materials capable of surviving neutron bombardment and control systems capable of responding in milliseconds. Fusion is not guaranteed to succeed within any fixed timeline, but the scientific principles are sound, validated by astrophysics and laboratory experiments. The question is not whether fusion releases energy. Stars prove that it does. The question is whether humanity can build a stable, economically viable system to capture that energy sustainably. In a world facing climate change, geopolitical energy tensions, and rising electricity demand from digital infrastructure, fusion stands as one of the most ambitious technological pursuits of our time. It combines fundamental physics with planetary scale implications. If realized, it would not merely supplement existing energy systems, it would transform the foundation upon which modern civilization operates.